Hello, my name is Kyle Ashbach, and I am an internal sales engineer with PR Electronics located in our Chicago office in the US.
My name is Chris McDonald. I'm a channel sales manager for the Western region in the US.
And today we want to go over RTDs and thermocouples. These are two of the most popular temperature sensors out there. We want to dive into the advantages and disadvantages that each one offers, as well as hopefully by the end of this, give you some clarity on which one is the best fit for your application. So starting off with RTDs, what is that? So stands for resistance temperature detector. In that name, you can kind of tell that it basically measures temperature by the resistance of the metal that's being used. For RTDs, there's really three main types that you'll see, and those are platinum, copper, and nickel. The reason these three are mostly chosen is due to their direct relationship with temperature. As temperature increases, the resistance is going to increase. As temperature decreases, the resistance is also going to decrease. In addition to this, how we actually measure the temperature is by sending a current through the sensor. This develops a voltage, and then when temperature changes and resistance changes, the voltage is also going to change, and that voltage change is what is actually being measured here to get our temperature readings. So going into a little bit more detail about the different types of RTDs, I've already mentioned that platinum, nickel, and copper are the three main options. Of those three, platinum is by far the most popular. This is due to the wide range in temperature that it offers, along with the corrosion resistance and long-term stability it offers, which are both very good. Nickel and copper have some advantages of their own, and those can also definitely be used, and those will also come at a better price too if that is important for your customer.
So Kyle, we know that a PT100 and PT1000 are both popular choices. Do you think you could explain a little bit about the difference between a PT100 and a PT1000?
Yeah. And so the difference between PT100 and PT1000, the first part of that PT is platinum. So they're both made of the same material. The difference comes here in the table, as you can see, the resistance at 0 degrees Celsius. So the one we have here in the table has 100 ohm resistance. This is a PT100. A PT1000 would have a 1000 ohm resistance at 0 degrees Celsius. And that is the difference that you see in any of the different styles, PT100, PT50, NI50, so on and so forth. Where this really takes effect and makes a difference is that when change in temperature occurs. So as you can see with our PT100 sensor, we have a 38.5 ohm resistance change going from 0 to 100 degrees. This is a pretty good change. This is something that your typical transmitter or input card are going to be able to detect. But if you wanted something even better, we would go with a PT1000. With that PT1000, we would have a 385 ohm resistance change going from 0 to 100, 10 times the amount of a PT100. Another difference between RTDs is going to be the number of wires that you use. So looking at a 2-wire RTD first, this is the simplest and the cheapest version out there. The reason for this is there is some issues that can come with this type of RTD. These 2 wires that are being used to connect your RTD element to your card or transmitter are going to have a resistance of their own. And so when we look at this RTD here, we've already noted that going from 0 to 100 degrees is going to be a 38.5 ohm resistance change. That's pretty small. So any extra resistance change that we might detect can make a huge impact on our temperature reading. In this situation, we have measuring boiling water at 100 degrees Celsius. So we know that we should be getting a 138.5 ohm reading. But the wires that we're using are running across to the other end of the factory to our card. And because of that long run, each one of these wires is adding 10 ohms of resistance. So with a 20 ohm additional reading, and now that we're getting 158.5 ohms, that's going to increase our temperature reading by 50 degrees. Doesn't really take a lot to realize that's going to cause some major issues. So really, 50 degree difference is usually going to not be ideal for your situation. This can be manually solved by actually measuring the resistance in your wires and subtracting that from your reading, but that's very time consuming and very inefficient, especially when you're dealing with a lot of different measurement points.
Okay, we know that the PT100 and the 3-wire is one of the most popular. Can you explain a little bit about what a 3-wire is?
Yeah, so how we fix that is by adding that third wire. And the reason this is the most popular is it's a great fit in between price and accuracy. It is going to be a little bit more costly than any 2-wire, but the benefits you get from the accurate readings from this is very beneficial and worth that cost. So what this third wire does is it's essentially a sense wire. This sense wire measures the voltage at the RTD element, and since there is no current being sent through that wire, we're able to get an accurate reading of the RTD voltage at the RTD element and not have to worry about the voltage drop that is occurring between our 2 lead wires. So this allows your car to transmitter to essentially subtract that difference from those lead wires and give you the accurate reading that you're looking for. There is an even more accurate version of an RTD. That would be a 4-wire RTD, adding a 4th wire here at the bottom, just an additional sense wire for both lead wires. This is the most accurate RTD out there, but also, again, by adding a wire comes an increase in cost. Typically, it's not worth it for customers to add that price for that extra level of accuracy. You'll only usually see these in chemical labs and pharmaceutical situations like that.
All right, thanks, Kyle. So now we're going to look at the other popular temperature sensor, and that would be a thermocouple. So a thermocouple is simply 2 wires that are of dissimilar metal. When you apply heat to one end of a wire, the free electrons are going to migrate over to the cold end of the wire and create a more negative charge. So that is called a Seebeck effect, named for Thomas Seebeck that discovered it. So different wires have a different Seebeck effect. Example we have here is the yellow wire and the red wire. The yellow wire has a much slower migration of the free electrons to the cold side, so it will have less of a negative charge. Where, on the other hand, the red wire has a very high level of migration from the hot to the cold and will have a higher negative voltage. So using the Seebeck effect, you can then compare those two and create a millivolt signal that is then goes to a temperature transmitter that is then sent to the control system, the DCS or the PLC. So since they're all different as far as their Seebeck effect, you can match different types of wires to get a different temperature profile. So now that we talked about the wires themselves, let's talk about what an actual thermocouple is. So it's 2 dissimilar wires. They're typically welded or married together, and that's what's called your hot junction. And this is on the positive side, so they'll share the same positive, and that's where the contact is made with what's being measured or an inside of a thermal well. So off of these 2 wires, you now have your Seebeck effect. In order to get that to a temperature transmitter, you will have to connect that to the terminals on a transmitter. Now the issue here is you have 2 different metals here, and the terminals are typically a chrome-plated steel. What that does in effect is add a 3rd element to this, changing that Seebeck effect, and now you have a cold junction voltage. The cold junction voltage is a mask, so to speak, over what the true value is coming over from your thermocouple. The good news is you can eliminate that with a CJC connector or the CJC on the inside of the transmitter. The difference being this is the internal CJC or the external CJC. To have higher accuracy, you want to remove that effect, the cold junction effect, at the closest point of contact. So by eliminating that, you now have a cold junction compensation.
We know we have 3 different types of RTDs, platinum, nickel, and copper. How many different types of thermocouples are there?
Yes, there are quite a few. There's at least 13 different types of common thermocouples. You can see here the J and the K are the most common. And by common, I mean 80 to 90% of industrial applications will use a J or a K type thermocouple. you can see it has a very wide range, minus to 100 to 1200 degrees Celsius, up to 1372. So between those two, that's most commonly used in the industry. If you have an extremely high temperature measurement, the W3 or the W5 have a 2300 degree Celsius. So anything over a 2000 degree application, those would be the most appropriate for. So let's go over some of the pros and the cons associated with thermocouples. So first is the high temperature range. So what we just covered with the different types of thermocouples, depending on your application, you'll match those, but they have a much higher range compared to an RTD. Response time, they're connected directly to what's being measured, either the element itself or the inside of a thermal well, and you have a very fast response time from direct sensing back to the transmitter. And they're usually less expensive. Most of this relates to the cost of the wire. A nickel wire or a copper wire is a lot less expensive than running a platinum. So there is a significant cost advantage with the thermocouples. On the con side is they're not very linear. A thermocouple will, instead of being a point to point like an RTD, there's actually sort of a curve that goes above and below from the top to the bottom. So you'll have a variation in that reading, and what you can do with a temperature transmitter is you can do a multi-point linearization, and that will bring it closer in line with what the actual measurement is. So when thermocouples are used in high value applications, you can supplement the precision and the accuracy with the multi-point linearization. They also can require the CJC. Depending on how accurate you really need to be, the CJC is there's gonna be some error from cold junction. So if you have a higher requirement for that to be removed, then the CJC connectors or the internal has to be considered. They're also very susceptible to electromagnetic interference and ground loop errors. So this wire could be running over a distance, and any electromagnetic interference or the ground loop errors will go directly on to the wire. The good news is the temperature transmitter is designed specifically to remove any of those. So ground loop errors and EMI can be eliminated, cleaning up your signal completely, isolating that, and again, cleaning up the signal. And then finally, sort of the loss of accuracy over time. You will see a thermocouple start to drift, and that's due to the age of the thermocouple. Again, we're looking at very high temperatures. They're in direct contact with those temperatures, and the wire itself just simply will break down. And one of the indicators is the drift that you're going to see over time. And that's one of the reasons too that thermocouples are replaced more often than you would see an RTD.
And so looking at some pros and cons for the RTDs, the pros are really going to be focused and regarding with accuracy. RTD generally is just going to be more accurate than a thermocouple. On top of that, you're not going to have to need any cold junction compensation or anything like that to make sure your RTD works correctly. And finally, the EMF, electromagnetic interference. RTDs are much more immune to that kind of interference than a thermocouple. So if you're ever in the situation where you're using that, you can be a little bit more rest assured that your RTD is reliable and giving you a good temperature reading. Of course, all those benefits that come from accuracy, that's going to drive up the cost. And that's one of the cons of the RTD. It is going to be more costly typically than your standard thermocouple that you're going to come across. In addition to that, anything over 850 degrees Celsius, it's typically the highest you'll see an RTD go to, is pretty much going to rule the RTD out. So if you're dealing with high temperature, there is really kind of no further decision to be made. You're going to have to use a thermocouple. And finally, the response time on an RTD is a little bit slower. So it can be pretty fast, but if every single millisecond counts for you, the thermocouple would be the better option. So now that we know the pros and cons of RTDs and thermocouples, let's take a look at a few applications and kind of see what's our best fit. So looking at our first application, we're dealing with a high voltage disconnector. We have an anti-condensation heater here to make sure that there is no moisture that is developed with the drive cabinets for lower temperatures. So just based off that, we kind of have an idea here that one, we're going to be dealing likely with a lot of electrical noise. We have high power kind of running through here, so that's going to be an issue that's going to have to be dealt with. And then two, the temperature here in this natural environment, we're protecting against low temperatures more than high, so there should be no extremely high temperatures that we have to worry about at all. Now we could dig a little bit further into this, and you should do that with all your customers. Is accuracy, how important is that to them? Response time. What's their budget? How much can they afford for a temperature sensor before you make a final decision? But based on these two main points, we can kind of start seeing what is likely going to be our best sensor here. So if you're looking at this application and you're thinking to yourself that an RTD is the best fit, you would be correct. RTD, very good at dealing with the electrical noise that we would potentially deal with here. And also, since we're not dealing with any kind of extreme temperatures, we don't have to worry about it being outside the range of an RTD. Again, you could confirm this by asking your customer questions. How important is accuracy? Very important. They have a higher budget. If all those things are true, we can stick with that RTD option. So this was an easier one. Let's look at another application here with Chris that might be a little bit more difficult.
Yeah, so here we're looking at a gas-powered heater. The gas is fed in and it needs to be regulated to maintain the correct temperature. So within the heater, it could be a furnace, could be a kiln, anything with a higher temperature range. These high temperatures need to be maintained within a pretty tight tolerance to maintain the quality of the production of the material that this temperature is needed for. So one of the main ones is that it's a very high temperature range that you're talking about. So furnaces, kilns, and these gas power heaters can get extremely hot. Second is that they need quick readings. So they need a fast response time to make sure that that temperature is maintained within the tolerance that's needed for the product that's being manufactured. And then finally, accuracy. So you can have the fast response time, but you also need the high accuracy so that you're responding correctly to the temperature reading that you're receiving. So in this application, we would take the thermocouple or the RTD and compare that to this application, see if that's what's right for you. So the first requirement here is for a very high temperature. So we know that a RTD is limited to 850 C. If you happen to fall within that range, then the RTD is probably a good viable choice. But the thermocouples can be 2 or 3 times the temperature range that an RTD is capable of. So as far as the high temperature is concerned, the thermocouple is a good choice. The second is the speed of the readings or the response time. So we know that the thermocouples are connected directly to what's being measured, so you get the fastest possible response time. And we also know now that the RTDs have a slower because they're not in direct contact with what's being measured. So having said all that, the thermocouple is probably the right choice, but really you want to go and compare those 3 requirements with the different elements that are available and hopefully help you find some success in your application. So we want to thank you guys for taking the time to stop by and see us. If you have any questions about RTDs, thermocouples, temperature transmitters, anything in those areas that we can help you out with, we'd be happy to do so. Just feel free to reach out to us. So thank you again.
Thank you, everybody.